Good afternoon. Welcome back. You can see that we're today recording the tutorial a little bit later. I recorded a version of this tutorial earlier, but it wasn't up to the quality that I was thinking, so I just figured I would go back and re-record a little bit of a better version, so we can get a better intro into and reiteration of groubits and what we can discuss in tutorial related to that and related to the assignment coming up. So, just before we get started, I wanted to bring your attention to a little bit of the change tutorial. Last week, someone brought up something that I wasn't aware of, that there was marks associated with the tutorial. So after some discussion and clarification, we've decided that there will be participation in the tutorial and participation marks assigned to the tutorial. So that's my bad for not clarifying this before. Me and Dr. Sarber came to arrangement, so we decided to just be fair, that everyone should get marks for all the past participation in the tutorials, but going forward there will be participation-based marks, which means if you are actually coming into the tutorials in person and you could participate in the conversation, then you will just get marks for coming in and doing participation. For those that are going to be going online, I will be opening up Avenue discussion boards, where you can either you'll have to post a short summary to show that you watched the video, and then ask any questions, give any feedback, comments, or anything related on the tutorial, related to class, just so I could tell that you're watching the recording and then you're engaged with the content, so that we can know that everything is going according to plan. And that's how we'll be working participation. And also going forward, there may be more tutorial-based assignments and questions, but for now they'll be on a case-by-case basis. So yeah, for this tutorial coming up, there will be discussion posts that will be due this Thursday at midnight, and I will reiterate those and put those on Avenue as announcements. But if there's any comments, questions, or concerns about that, feel free to reach out to me on email or put it on the discussion post as part of your participation. So the way I was going to start at this tutorial is if there was any questions or follow-up from the midterm. The midterm that you guys had last week, hopefully everyone was pretty straightforward and did pretty well. So I'm not going to take up any questions, as none were particularly asked. So hopefully everything was straightforward enough that everyone found it good. If there was any questions and wanted any of the midterm questions to be worked through, feel free to reach out to me, or to reach out to Dr. Shabri, or I can work these out as part of the next midterm if anyone had any, or it's the next tutorial, if anyone had any particular questions about how to work out any of these. But hopefully they were straightforward. Most of you did pretty well, so that is probably absolutely fine. So now on to the tutorial for itself. So as you can see, as Dr. Sabri posted in class, assignment 4 is nearly coming out, and this is all on super dense coding and teleportation, but you're doing them classically. So let's actually, I had to prepare a little bit before, so let's get into a little bit of the notes that I had before. So a lot of this is taken from the 19th lecture, and I'll just be going through a couple different things just around, let's make sure that we do the relevant justification for why do we have groubits, and then how do they work, and what are some of the different operations that we can do on them. So in the last one of the lectures, we talked about the Grossman-Nil theorem, where we said that any circuit from H, CX, and S, which is swap, could be built and simulated classically, which means that if there's a classical efficient simulation to this, where's the quantum advantage coming from? Maybe it's coming from the fact that we don't have Toffoli in there, so we don't have a universal set of gates. But if many of these algorithms, such as the Deutsch teleportation and the supercondensed coding, can be done classically, why don't we do them? So this is getting into actually going to do them, and that is through QSLs or groubits. So some people like to call them QSLs, and some people one of the possible interpretations of that is qubits. And QSLs, I know I wrote it down here, so let me just make sure I found what QSL stands for. Quantum simulation logic was it. So QSL stands for quantum simulation logic that we can use to simulate these quantum effects classically. So if you remember, I'll skip back and kind of zoom in to make everything. So we have in a groubit a bit that is two sets of bits, and it could be 0, 1. And you may be wondering where groubits come from. So actually there is a paper assigned to it that you're not required to read, but I'll bring it up just as a examination. So this paper is actually very simple to find, because if you search up groubit, you won't get a whole lot. So let me search up quantum mechanics groubit, and there is not a whole lot of searches that relate to that, so that's how you know we're getting into some good stuff. So the first paper there is on classical groupoid model for quantum mechanics, and it deals with exactly what we're working with, which is groubits, and network architecture for things including teleportation, dense coding, and secure key distribution. So if we open up this paper, let me just throw this up into the screen and let me go to the top. So this is the paper that we just downloaded from that website, Classical Groupoid Model for Quantum Networks, by Reuter and Vicari, which I'm probably not pronouncing right. But this paper, I wouldn't suggest reading all of it. It gets pretty dense pretty quickly. But what it does do is do a good introduction into like groubits and how they work. So as Dr. Sabri has talked about in lecture, there's generally two different types of bits there's two bits associated to every one quantum mechanical bit. In here, they denote the first bit as a logical bit and the second bit as an internal bit, AI and AL correspondingly. And then there's several options that are associated with these, operations. There's the init, swap, read, write, and tick, and those are considered some of our primitive options that are in there. And for example, to try and simulate some of these quantum behaviors, we're going to use some of these bits are going to be random, and we will not be able to access and know what they are necessarily without doing the actual going through these procedures. So that's going to be one of the properties that we're going to go over. But let's take a look at some of these 5 initial procedures, and we'll go from there. I'll put this on the side of the screen, and I'll go to some of my slides. Hold on, if I can make this look nice. So those are our 5 procedures, and they're outlined here in the introduction, the 5 different procedures, but I'll also just give a different interpretation or a different writing of them, so it's just maybe possibly easier to follow. So tutorial 6. So here written we'll start with our swap, which is probably pretty intuitive. If we have a groubit of A and B, after we put it through the swap, it's just going to be B and A. So it just swaps the logical and the internal bit. The next one is, we'll get to actually tick last because it's the most interesting one. There's also the initialization of a bit. So this one is interesting because if you start from nothing, actually I should say that there's that to denote, as if I was saying that there's no input, we create a groubit that starts with a random number, like a random number not initialized to anything in the actual first bit there. And in the second bit, we create a false or a 0. So in this case, I'm actually just going to call it a 0, just to make it more explicit that we're dealing with 1s and 0s because they're bits. So in the actual logical bit, there's a random number when you initialize one, and then there's a 0 in the next. And you may wonder why we actually did this when we consider initializing a bit. And I do not know based off of that why, but I'm sure there's good reason. And you could also just think of this as a general function that just gives a generic bit that is starting with any random. So it's either 0 or 1, and we're not sure what it is. Then we have our 2 read and write operations for groubits. The most importantly is the read is where you take a groubit that's made up of A and B, and then it just reads to a classical bit A. The other important part, and I'll make this full screen just to make sure it's important, is in the process of doing so, we destroyed the groubit. And by destroying the groubit, we mean that we can no longer interact with it or access any information or measure it. So in this act, we measured it, and the groubit is completely gone, just with the normal quantum mechanic measures, and now it's fully converted to its logical bit there, we should say. Now, in the same sense, we can also write to a groubit. So if we start with a classical or bit A, we can write it where the logical bit is in A there, and then the actual second bit or the internal bit becomes a random number, and there I just call it random B to designate it's a random B portion of the actual bit, it's like groubit itself. And in this case, also the A or the classical bit gets destroyed. So creating groubit from a classical bit. We always have, no matter what we do, there's going to be some random component to it, whether we just initialize it and we know what the internal state is and the other state is random, or the other bit is random, or we create it knowing what one bit is and then the other bit will always be random there. So then now we get to the last and the fifth of the functions here, which is the tick bit, or the tick groubit. So it's also described in the paper. All these are, like I said, described in the paper as well. But this does something quite interesting, and I'll put it in both forms just to show that they're equivalent. So when we have two groubits together, each with their own logical and internal bits, if we do a tick operation to it, what happens is the logical bits stay the same. So here outputs, the logical bits are the same, but the internal bit of the first one and the logical bit of the second one get XORed, or also you could say that they are added together, or you could do the not equals operation to it. And same with the second one. The internal bit is XORed with the logical bit, or it is here, the plus is in addition with modulo 2. So it's, addition and then modulo 2. This is also, you could think of, and I'll pull this over to the side just as you can see. So it's like flipping the internal bit when the other logical bit is equal to 1. So the internal bit gets flipped whenever the other one's equal to 1. Now that number may be random, so the internal bit may be random and the logical bit may be random, so we don't know exactly whether it's equal to 1, so it's just an operation that we can do to kind of couple these two together in a sense. So yeah, don't worry about think it's a form of graph topology, but essentially that's what tick does, is it couples these two bits together essentially. And so that'll become a pretty important operation there. So now this is where we're going to diverge slightly from the paper, mostly because the paper gets into some really interesting diagrams of graphical calculus real fast that I'll scroll down. I'm sure it would also that would not be the worst amount of your time or the worst use of your time to read this paper if you really want to try and understand more and see what the research writing is about, but it gets very interesting very fast. So I would suggest just sticking to the first part. There's one more thing that we can glean from the paper though, and I'll scroll back up to the top, is the assumptions that we make about these groubit operations. The first is that they're atomic, which means that they either succeed or have no effect at all. And if they do succeed or they don't have any effect, you do know what, both the parties, meaning us, know what actually has happened. So we know that if we perform an operation, we know that it succeeded, or we know that for some reason nothing has happened at all. So we do know that for sure. And the other assumption or property that we have about groubits is that the state of the node can be accessed except via read, or there's another operation later that we're like any derivatives using read. So that means that unless we do the operation where we find the first logical bit variance read, there's no way we can know what the state of the groubit is, analogous to quantum mechanics where we don't know the state, or the combination of alpha 0 plus beta 1, or whichever it's written. We don't know it until we actually measure it, and even then we can't know what is actually going on with the other bit. So this groubit QSL is basically something that will make it very analogous to quantum mechanics without having to actually deal with all the trickeries of the quantum mechanical hardware. So in your assignment this week, you can see that this kind of formulation is gone through in the same way. where we talk about, sorry, I'll scroll down to where he explains groubits and how all these different operations work with the swap, ctick, which is a special case where it's just a one case of tick and an actual normal tick. Here, Dr. Sarbury denotes the right arrows to be going from one state to another. And then here it's going from, a function in like being input into some certain groubit. But there is a couple things that you might want to know, that there are some other types of functions that are talked about in the paper, which we can talk about really quickly. And I will slip over to those. And then we'll also I'll give you just a couple pointers to where to look at in the actual book itself, the textbook, on working with the superdense coding and the teleportation. But first, let's take a look at a couple different operations. So the syntax is going to be a little bit hard to read, but I will walk through just a little bit of a trace of these that you can look at yourself as well. So there's another operation that we have called iReadG for iRead or the groubit, and here, instead of reading the A of the bit, it's going to read. It's going to swap it first and then read the B of it. So the actual procedure, you could see, might think if we wrote it, you could use left as an exercise that you can write it out using something like this notation. But first we swap the actual bit itself, and then we read this swapped bit to get an actual B out. So that is an iRead of the groubit, and that's just reading the B instead of an A, essentially. Then there is another, sorry, I'll just delete these annotations here. There's another form of click that we're going to use, which is called ctick-g. Here, what we're going to produce in the end is, so we're going to take a variable in A, and then we're going to combine them and basically write to a groubit. So now we have a groubit of A and a random B. And then we're going to take another groubit that we've input into ctick-g. So I'll just say as the inputs, we take an A, and then we take a G bit of C and D in there. So then we are going to do a normal, let me make sure I get that right. We're going to normal do a tick-g of the qubit we just wrote and the one that we take from input. So here we combine them so that we have the internal bit crossed with the logical bit of the other groubit, and then for the internal part of the next one, we have the internal part mixed with the logical, the first one. So we've done a tick operation here. So we've done write tick, and then the next part, we take the resulting first bit that we created after the first or qubit we created after, and then we're going to actually read that out. So we take this and we read an A, and we're going to combine that with the second part of the second groubit that we had here. And this is actually going to be our output, which is our initial A, and then the groubit A, but with the coupled in part here. So we take this and there, and our classical bit that was read back. So that is ctick at the end there. So this does a couple operations, and it's useful for different situations. And the last one, or the last operation or helper operation that we're going to have is split G here. And split G is we're going to initialize a bit. I'll get rid of these annotations here. Initialize and tick. So we're going to initialize a bit. So we're going to groubit, and we're going to get rand and 0. Then we're going to do a tick operation between that groubit that we just initialized and a groubit that is input. So I should actually say as input, we take a G bit of A and B. And also, just to be clear, let's take a G bit A and B. I'm sorry that I'm not being very consistent with my notation, but hopefully you get the idea. Close off these parentheses. So here, now we're doing a tick operation between our input groubit and our initialized groubit. And so we get this combination of the groubits and the having the different components here. We're going to get the and mixed with the internal bit of the first one, and then we're going to get the A component of our input one mixed with the 0 there. So that split operation is then going to, sorry, that's my bad. The split operation is going to output these two groubits themselves. And so then there's a third operation, which actually is covered over in the assignment, and that one is the entangle one. So we can go through and see here that this operation entangle is where we take and initialize two different bits, both that have randoms, and then we do a tick between them, and then we swap the two. And that is actually how we go forwards and create our actual different operation of entanglement. And you can see if we were to write it out and trace it out, how that would actually work. So for your mini assignment that is going to be due for this tutorial 6 this week, is to write Python versions of all these. In your assignment, you're going to have to actually write these protocols in Qiskit anyways. So as part of that, what's going to be due on this Thursday is for the 5 primitive operations. I would like a Python or a Qiskit, not implementing Qiskit, but a Python notebook or just Python script file implementing these 5 things, these 5 operations, and obviously the base type of groubit. No need to create restrictions of any kind so that you can't read them, just create the 5 different functions. And then that'll not only be useful that you've written them out, and that you can use them for your assignment when you actually implement them and implement different protocols in Qiskit itself. And implement the assignment in Qiskit itself, I mean. So, I did say I would have a little pointer for the textbook for any of those that wanted a different interpretation or a different writing and a more formalization of super dense coding and teleportation. So if you go to, let me go to the contents of the textbook, chapter 5, section 5.31 and 5.32, which is page 80 of the textbook. We'll go there. So let's actually scroll down all the way to the bottom. So application of simple gates, 5.3, blah, blah, blah. Then we get to super dense coding. So if you wanted to either follow along using Dr. Sabri's logic or having the textbook analogy textbook explanation of it, there is 2 different sections on super dense coding where we go through the same logic. It's just also, remember, it includes the 1/2 factor because we dropped that in our explanations just to make it easy to write, but it's still there. And then there's a explanation of quantum teleportation with the same sort of diagram in the EPR source. Now it doesn't have the circuit, like we go over in class, but it goes through and gives a brief explanation of how that all works. Just as it goes over the same logic, a little bit more condensed than what we did in class. But if you did need a reference to source for how you're actually going to create these, definitely for the assignment, make sure to definitely either use the Dr. Sabri's method, Dr. Sabri's reference, or the textbook as a reference. And yeah, if you need any more explanations of how groubits work, I suggest looking at least at the start of this paper, but this explanation here is also pretty sufficient. So yeah, for this this Thursday at midnight, what you're going to have is a participation in an Avenue discussion board. The reminder that now we're going to have participation for all the tutorials going forward. And then I would like a Python implementation of the 5 basic operations, init, read, you don't need I read, write, and then swap. And then tick as well. Sorry, that is the 5 that I had listed here. Right. And also groubit, obviously, because you're going to need a groubit type to start with. So yeah, these 6 things essentially. All right. Well, that is the tutorial for this week. Kind of a quick one, but it's also, you got something to do and then something for tutorials or something for your assignments coming up. So good luck with that. And if there's any questions, please feel free to post it on the discussion board. Thank you very much. See you later.